In this lab, we're going to use BigQuery to build a linear regression model on around 10 years worth of Apple stock data. There are several objectives for this lab. First, we're going to import the stock data, stored in Google Cloud Storage, into BigQuery. Then, we're going to use this data to actually build and evaluate a regression model in BigQuery. Let's get started. When you first boot up the lab, you'll land in the GCP console landing page. I like to find whatever service I'm interested in by just navigating to it in the navigation bar on the left here. So BigQuery is stored under the Big Data header. Go ahead and click on that. Okay, now we're in BigQuery. So the Apple stock data lives in Google Cloud Storage. To get it into BigQuery, we first have to create a place for it to live. Let's go ahead and do that by creating a data set and a table. So to create a data set, you first click on your project name here. I'll give you the option to create a data set. We'll leave most of the defaults. The only thing we have to provide a data set ID. In this case, we'll call it AI4F, AI for finance. And we'll click on create data set. When the data set's created, you'll see it here. Then next, we want to create a table. So to do that, you click on this plus icon, create a table. And the main thing here is our source is going to be Google Cloud Storage. So we'll click on that, and then we have to provide a path to the GCS bucket where our Apple stock data lives. So go ahead and do that. And again, we're going to leave the defaults pretty much, except we do have to provide our table with a name. We'll call it AAPL 10 year, since we have about 10 years worth of data. Then the only other thing is, since our schema is specified in the CSV file, we'll want to go and have BigQuery auto detect that. So we'll check this icon here. Then we'll click on create table. And then you'll see after a few moments that your table here is listed under your data set, which is listed under your project name. You can view the schema of the table that we created by selecting it from the drop-down menu. So here you see field names for date, close, volume, open, high, and low. And also I'd like to point out that everything that we're doing here using the BigQuery graphical user interface can also be done using command line arguments. Sometimes those are really convenient. So I'd like to start by viewing the first several rows of whatever tables I'm going to be working with, just to get a better feel for what's in them. So we'll go ahead and do that. Execute the query. Okay, so it looks good. Let's go ahead and write some more complicated queries. So in the lab, we're asked to find the minimum and maximum of the dates in the data set. Let's go ahead and write the query for that. So this is pretty straightforward. All we'll need, the date field contains the information we need, and then we'll just apply the minimum and the maximum functions. This is what the query looks like. We'll run it. And then here's the result. So the minimum date is June 3rd of 2009, and the maximum date is June 3rd of 2019. So kind of as expected, there's a 10-year separation between the minimum and the maximum dates. Now, for a more challenging query, we're asked to calculate the average closing share price for each year. So go ahead and compose a new query. Now, to do this in SQL, we need to aggregate our data by year using the group by statement. Since we're grouping, we need to apply an aggregation operation in the select statement. Since we're interested in the average closing price, that's the aggregation we'll use. In our query, we'll also order the results by year in descending order. That's achieved using the order by statement. So we'll go ahead and run our query. And we have the results. No surprises there. Finally, we're asked to answer the question, which 5 dates correspond to the greatest % increase in Apple stock? So we'll go ahead and compose a new query. So to find the answer, we need to write a query to output the % increase in the previous day's closing price. One extremely useful SQL function that will help us is the lag function that you see here. So basically, the lag function can be used to reference previous rows of data in your table. We need the previous day's closing price, and so the correct syntax here is lag, close, and this 1 signifies that we just want to look 1 day before. We'll tell the lag function how to order our data in the over clause. Here we order by date. The lag function is really powerful. You can actually apply the lag function to groupings in your data using the partition clause. I encourage you to check out BigQuery's lag function documentation to find out how to do this. So we'll just take the current row's closing price and divide it by the previous day's closing price to get the percent increase and multiply by 100. We'll then order by these changes using the order by clause here, and we'll just limit to the top 5 results. We'll go ahead and run the query. And here we have the results. So it seems like the greatest percent change was around 9% or so occurring in the year 2012. So now that we've explored our data a little bit, we'll move on to the most exciting part of this lab, where we actually build a regression model in BigQuery to predict the closing price of Apple stock on any given day. So our model will be really simple in that it only has 2 features as input. The first feature will be the previous day's closing price. That makes sense to me. The second feature will be something we call a 3-day trend. The 3-day trend variable for any given row looks at the previous 4 days' closing costs. If the closing price on a day is greater than the closing price on the previous day, then we assign that day a positive 1. Otherwise, that day gets assigned a negative 1. Now, if the majority in the past 3 days consists of positive 1s, then the 3-day trend is set to positive 1. Otherwise, it's set to negative 1. So let's go ahead and look at the query that will get us the features that we're interested in. So we'll go ahead and compose a new query, and we'll paste in the query from the Quick Labs documentation. So to get at the features we want, we're going to use 3 subtables. And we're also going to make heavy use of the lag function that we just described. So in this first subtable, we extract the closing price directly, which we'll use as one of our features, and then we apply the lag function 4 times. The first one we look 1 day before, and the second lag function we go 2 days before, and so on. And we need to look 4 days before so that we can create that trend 3-day variable. In the next subtable that we call raw plus trend, we're taking the output of the raw table, and for each of the previous 4 days' closing prices, we're looking to see if the closing price increased or decreased. We create 3 new columns. In the first column, min_1_trend, we assign positive 1 if the closing price increased and negative 1 if it decreased. Min2 trend does the same thing, but it looks 2 days back, and min3 trend looks 3 days back. Finally, in the ML_data table, we select everything we'll need to create our ML model. So close is what we're trying to predict. Min_1_close is the previous day's closing price. And here in this if statement, we're basically aggregating the previous 3 days' trends. So we're using the if statement as kind of a max function. If at least 2 of the previous days have increased in close value, then we set this to positive 1. Otherwise, it outputs negative 1 for the trend_3_day column. Now, rather than just running this query, we're actually going to save the results to a table so that then we could use as input to our ML model. So to do that, we click on More, Query Settings, and we'll leave most of the defaults except for this destination. We'll set a destination table for query results, and we'll save it to the same data set we created earlier. We'll call the table in which we'll store the output model data. Then we click Save, and then we execute the query. We see here that the table has been created, and we could just scroll through some of the rows to look for correctness. Okay, everything looks good. To build the ML model, we'll go ahead and compose a new query. So here's the syntax. The first line tells BigQuery that we want to call our model AAPL_model, and that we want to save it to our dataset AI4F. The next few lines describe some of the parameters of the model. Namely, we want a linear regression model. We specify the continuous variable we're trying to predict, which in this case is close. We also specify some parameters for how we want to validate the model. We don't want to validate our model on the same data we use to train our model. For validation, we tell BigQuery to split our data sequentially, since we basically have a time series. We also tell BigQuery to use around 30% of the data for validation purposes. After we tell BigQuery about the type of model we want to build, we show it the data we want to use. We already created this data and stored it in the table model_data. So here we're just plucking out the features and target variable. We'll go ahead and have BigQuery create this model by executing the query. This could take several seconds here. When the model is done, you'll see it here under your dataset. Now, to see some evaluation metrics, you can enter the following query. Since we trained a regression model, the main metric to look at is the mean squared error. Note, your results may vary a little bit. The mean squared error takes the difference between your model's predictions and true values, squares them, and then adds them all up. Based on this mean squared error value, our model is not very good. Then again, what do you expect when we only use two simple features as input to our machine learning model? Finally, now that we have a trained ML model, we want to make some predictions with it. Let's compose a new query where we have our model predict closing prices for all dates in 2019. So here's the syntax. Let's run the query. Now, just as a sanity check, we expect the predicted close values to be similar to the previous day's values. We can visually inspect this by scrolling through some of the predictions. Sure enough, that's the case, but this doesn't mean our ML model is any good, as we saw by looking at the mean squared error. It can be improved quite a bit by creating some more sophisticated features. Go ahead and try to create some of these yourself. Be creative.